Okay, so for this next question it says, based on what you've seen so far, does f of a have to be defined? So remember, for it to be defined, it's like the points closed in order for the limit as x approaches a of f of x to exist. And it wants us to draw and explain two different graphs to justify our reasonings. Okay, so think about the graphs that we've seen. Let me just pull up a few here. So we looked at, on example 2, we saw here that this limit existed, but it was defined here. Okay. Some other examples. This limit exists, it's defined there, but not there. This limit exists for this number where it's defined. This limit doesn't exist, but it's defined. So, the moral to that story is it being defined does not mean that the limit necessarily exists. Okay? So, no, it does not have to be defined. Now, let's draw that to figure out what in the world that actually means. But so, no, it does not have to be defined. Okay, it says, in our graphs, we want to, f of a should be undefined, but in one graph, the limit exists while the other one it shouldn't. Okay, so here's just an example. Draw a graph. I'm going to call this point right here A. So I'm going to put a hole here at A because it says it wants it to be undefined. And I'm just going to draw my graph like this. Okay, so it wants it to be undefined, so we can say f of A is undefined. But does this limit exist today? So if you go from the left and the right, are you approaching the same y value? Yes. So in the limit as x approaches a exists. Okay, so there's one example. Next example. This time we want to make it undefined, but we want to make the limit not exist. So do the same thing, we'll call this A. Okay. For it not to exist, we would have to have a jump there. So I'm going to put a hole here. Maybe the graph goes like this. I'm going to put a hole here, and maybe the graph goes, I don't know, like that. So it's still undefined. But now, because we have this is the left side approaches this y value and the right side approaches this y value, then that means the limit as x approaches a does not exist. Okay, so what I want to get from this, does it have to be defined? If I would have closed this circle in here, okay, and made that not a hole, it's still going to be, the limit's still going to exist. If I was to define this and fill in one of these holes, the limit's still not going to exist. So it being defined or not defined does not matter for the limits. Okay. All right. Last thing we're going to do is take a look at two different tables and figure out the limit from the tables. Now, personally, I think it's easiest if you kind of create a graph from the table and then go from there. But you just strictly can use the table if you want. And you have to read. It tells you. It's going to tell you when it gives you a table what kind of function it is, and that's super important because if you know what kind of function it is, you know what kind of features it has. So this first one is an exponential function. Okay, so hopefully you remember from pre-cal, exponential, it could look something like that. Okay, this is just some example. So exponential function. Exponential function is not going to have holes if it's a real exponential function, so no holes. But it is always going to have a horizontal asymptote. Okay, so exponential functions have no holes, horizontal asymptote. Now this can be flipped other directions, but that's essentially the shape that it is. Okay, so here's the information they're giving us. So they're telling us we have a really big number here. Like if you notice, it was like these are small and they're getting bigger here. So these numbers are going to keep getting bigger and bigger and bigger here. Okay, I'm going to put, they go towards infinity because they're getting bigger. Now these numbers, if you look, it's like 1.5, 1.125, 1.002. So those are kind of getting closer and closer to 1. Okay, so because we're talking about an exponential function, it really only matters with the end behavior, because everything in the middle, there should be no holes, so there's nothing weird going on. So the graph I drew actually will work for this. So it's like the left side's going to infinity, getting bigger and bigger. The right side's going to 1, so I could just draw in that, and that's a 1 there. Okay, so let's answer the questions. The limit as x approaches negative infinity. So they're talking about that left end behavior. Okay, the limit as x approaches negative infinity. So we said on the left side of this graph, these numbers are getting bigger and bigger and bigger, so it's going towards infinity. Just like my picture is up here. Okay, this says the limit as x approaches negative 3. So because I know there's no holes here, think about negative 3 could just be some point here. From the left and the right, you're approaching the same number. So because I know there's no points or here or no holes, then I know the answer just has to be the y value now. Same thing here. The limit as x approaches 1. Well, at 1 on your graph, there's also no holes, so the left and right are the same thing. So whatever the y value is what the limit has to approach. So if you know there's not any holes, then it's just the y value. And then the last one says the limit as x approaches infinity, so this would be our right end behavior. So we said as this graph, as the y value or x values keep getting bigger and bigger, on the right side of the graph it's approaching 1, which we said was a horizontal asymptote. Okay, so if they tell you it's an exponential function, the graphs are going to look similar to that. One side's going to either be going towards infinity or negative infinity. The other side has to be going towards that horizontal asymptote. And then, excuse me, there's no holes, so you're going to want to make sure that you see that it would just be the y value. Alright, the last example here is a little more intense. It's about a rational function. So we looked at a rational function on the very first thing that we did today. So if you need to go back and look, but rational functions have, they might not always, but they can have holes, they have vertical asymptotes, and they have horizontal asymptotes. Okay, so they can have all that stuff. Not as easy as the exponential. So we have to figure out what's going on here. So I personally like to draw a graph. I'm just going to kind of see what's going on here. So the first thing that catches my eyes is there's two places to say undefined. Okay, so those are key things that are happening. So what you want to look at, let's look at the -1 first. See how this is a really big number, 2001, and this is a really small number, -1099. Okay, -1999. So what this is saying is this is getting bigger and bigger. So this is going towards infinity, and this is going towards negative infinity. Well, what does that mean that we have? That means that you're going to be having a vertical asymptote at x equals -1, because one side is getting very large, one side is getting very small. Okay. So if I want to just go ahead and sketch a graph here at -1, I'm going to have a vertical asymptote, and I'll draw what that means in a second. Now at 2, this has 0.333 and 0.334, which is essentially the same number. So when they have the same number like this means that this is a hole here. Okay, and it's the hole at that middle number, so think about 0.333 is like 1/3. Okay, so at 1/3, we got a hole somewhere. Okay, or at 2, sorry, 2, we have a hole at 1/3. So go and draw that in. Alright, then we need to always look at the end behavior. So at the end here, remember it was like 2001, but now it's going to 1. And then over here, it's also going to 1. So when you have rational functions, most of the time they're going to be going towards the same number, which means that that number is your horizontal asymptote. Okay, so let's sketch this graph before we even start looking at these limits. So, alright, so we said at 1 we have this horizontal asymptote. We said that on the left side here it's going towards infinity. So towards infinity at that vertical. And then we said here it's going towards negative infinity. So it looks something like that. So guys, this graph is not required, but it helps me to picture what's going on. Okay. So if they tell you it's a rational function, the things that you need to make sure you look out for, you need to see if it says undefined, it's either going to be a whole or it's going to be a vertical asymptote. If it's really big numbers and small numbers, then it's going to be vertical asymptote. If it's the same number or close to it, it's going to be a whole. And then if they're approaching the same number on the ends, that's your horizontal asymptotes. Okay, so part A says the limit as x approaches negative infinity. So we're talking about the left end behavior. So we just said the left end of the graph is going towards 1, or if you want to look at the graph, it's going towards 1. Okay, I'm going to go ahead and skip to part E, which says the limit as x approaches infinity. So now we're talking about the right end behavior. Well, we said the right side was doing the same thing, approaching 1, or towards our graph is approaching 1. Alright, part B, the limit as x approaches negative 1 from the left. Okay, so here's negative 1. Here's the left side of the graph. We already said here it's approaching infinity because it's getting bigger and bigger. Alright, the limit as x approaches negative 1 from the right. So we already said these numbers are getting very small, so it's approaching negative infinity, which you can double check on your graph here. Alright, the limit as x approaches 2. We said there's a hole there, but remember, holes do not matter for limits. You can still have a limit. As you come in from the left and the right, you're approaching the same number. You're approaching that 0.333, which is 1/3. Okay. And then the last one, the limit as x approaches negative 1. Okay, well, we already said it comes in from the left and the right. It's positive infinity and negative infinity. Those are not real numbers, so that means this doesn't exist. Okay, and that's because the limit as x approaches negative 1 from the left and the limit as x approaches negative 1 from the right are not real numbers. And we can't have a limit that's not a real number. Alright, so that is our limits graphically and from a table. So you'll have some practice on that.